All right, the purpose of this video is to kind of take place of our lecture. So instead of being in class together on January 25th, this video is just going to substitute for a lecture instead. So what I want to do is quickly recall what we did last time. And so last time we saw that we could define the rationals as the set of equivalence relations over a set E, where E was the set of integers crossed the set of non-zero integers. And so then we defined a relation on E where two pairs of elements in E were related whenever A times D was equal to B times C. We saw that this was an equivalence relation. We saw that the different set of equivalence classes correspond exactly to the different rational numbers. And so we can define the rational numbers as the set of equivalence classes that E has given R. Okay, so this is E mod R. So this is the set of, this is called the quotient set, or the set of all equivalence classes. So that's a formal way that we can define the rationals. And then given the rationals, we talked about how to add two rationals and how to multiply. I think multiplying is easier, it's more intuitive. You just do it pointwise. So AB times CD is just AC comma BD. And addition is defined in the usual way that we add rational numbers. We talked about the defects of just adding straight across. That's called the median. It's not a well-defined operation. It doesn't respect equivalence classes. And so if you have two different values from the same equivalence class, adding does not give you the same value. So I think the example that we did in class was something like 1/2 plus 1/3 was not the same as 2/4 plus 1/3. They were just different. So anyways, the way that we add was the way that you would expect. So AB plus CD is AD plus BC, comma, BD. And it turned out this is completely well defined. It respects equivalence classes. This is the good definition. So this is how we define multiplication and addition. Okay, and then we talked about a few other things in class. So we talked about, we talked about how to add. I'm not sure how far we got actually, so let's just review a little bit. So let's talk about what's the additive identity. Oh, I know we talked about the fact that when you think of the rationals this way, the rationals were closed with respect to addition and multiplication. They are commutative because when you look at these different operations, these are just pairs of integers. And so we know that the integers are commutative. They're associative because the integers are associative. So you inherit a lot of the structure of the integers. You also get a distributive law, which works the way it does because of, again, that just inherits things from the integers. So let's talk about additive identity and the multiplicative identity. And so the additive identity turns out to be the number 0, 1. So that equivalence class, anything in that equivalence class, we can call the additive identity. And you can just check that if you take any number, A, B, and add to it 0, 1, following our rule that we have for addition, what we get is A times 1 plus B times 0. So we get A times 1 plus B times 0. So in other words, A, comma, BD. So that's B times 1, so B. So this is exactly the thing that we need so that if we add it to anything, it stays unchanged. It's the additive identity. It's the role of playing the role of 0. And likewise, the multiplicative identity is just going to be the rational number 1, 1. And so you can check that if you take any rational number AB and multiply by 1, 1, remember that we're just multiplying pointwise, so these really do stay unchanged. Okay, so that just becomes multiplying AB by 1, 1 just fixes it as AB. So those are the additive identity and the multiplicative identity respectively. We have additive inverses. Okay, so given, so for every rational number, So for every value a, b, there exists a value, I'm going to just call it c, d, so that when we add them, if I add a, b, and c, d, we get the additive identity. Okay, so for every value a, b, there exists a value c, d, so that it has this property. And of course, it turns out that our additive inverse is nothing more than negative a comma b. And you can check that if you take negative a comma b and add it to a comma b, you get 0 comma b, which is in the same equivalence class as 0, 1. That's for any non-zero b. Of course, we need b to be non-zero to talk about a rational number to begin with. So that's additive inverses. Now with the rationals, we get something that we don't for the integers. We also get multiplicative inverses. Okay, so every non-zero element, okay, so for every non-zero rational number, in other words, for every rational number that's not the additive identity, there exists another rational number, let's again call it CD, so that when we multiply them, we get the multiplicative identity, which is 1, 1. It turns out that the multiplicative identity here, the multiplicative inverse, is, let me write it like this. It turns out that the multiplicative inverse of AB, which I'm going to denote as AB to the minus 1, is just the rational number B comma A. Okay, and so if you think about the way that these are defined, when you multiply them, everything is fine. Okay, and so that's what you get there. So if you multiply these, you will get AB comma AB, where A and B are non-zero, and that's going to reduce to 1, 1. That's in the same equivalence class as 1, 1. All right, and so we get multiplicative identities where we didn't get that with the integers. Now, a few other kind of remaining questions. I want to know in what sense is the set of integers a subset of the rationals, right? The rationals contain the integers, and it turns out that you can take every rational number, every integer, and write it as a particular equivalence relation. So given n, n is represented, we can think of n as being the same as n comma 1. Okay, so that's the sense in which the integers are a subset of the rationals. The other, I think, remaining question is, how do we order Q? If this is how we're defining the rationals, as this strange set of equivalence classes under this relation, how can we give it an order? And so in order to do that, what I want to do is I want to think about how did we order the integers? And so first, how did we order the integers? I know in class I said that basically what we do is we just use the usual notion of less than, which is true, but that doesn't help us here. It doesn't generalize. So what I want to do is I want to zoom in a little bit on this. And given two integers, let me first say that an integer x is positive when x is in the set 1, 2, 3, and so on. So I'm going to call the positive integers the set 1, 2, 3, 4, 5, and so on. And then given two integers x and y, we write that x is less than y to mean that y minus x is positive. Okay, and that's a completely rigorous way to define a relation on the set of integers. Okay, now we can do a similar thing for the rational numbers. And so for the rationals, we're going to say that the rational number AB is positive when A times B is a positive integer. So now that I've kind of defined this relation for integers, I can use that. So we're going to say that the rational number A comma B is positive whenever the product of the terms is positive. Okay, so that's what it means to be positive. And then the ordering that we'll put on the rationals, we'll say that AB is less than CD when the difference CD minus AB. By the way, what I mean by minus is, just to be clear here, I haven't actually defined subtraction in the rationals, but I'm adding the additive inverse. So subtracting is just adding the additive inverse. So anyways, AB is less than CD whenever their difference is positive. Okay, and then positive just means that the product of the terms in that rational number, A times B, is positive as an integer. Okay, and so that's how we define the order on the rationals. There's other ways that you can order the rationals, like you can use a dictionary order, like comparing, say, the first value, the first entry in the pair, to the second entry. But the ordering that we use, kind of the usual ordering, is exactly this ordering here. Okay, and so this gives us kind of our usual notion of less than there. And so it turns out if we kind of put together all of these things, all of the properties that the rationals satisfy, it turns out that there's a name for such sets, and we say that Q is an ordered field. So what I mean by a field is basically that it has all of the properties that we talked about so far. I'm not going to write them all out, but the rationals are closed with respect to addition and multiplication. Addition and multiplication are commutative, so the order that we add and multiply doesn't matter. They're associative, so if we have 3 rationals being multiplied, it doesn't matter whether we do the first 2 first or the last 2 first. We'll get the same product. Same with addition. They're distributive, so they satisfy the distributive law. There exist additive and multiplicative identities. There exist additive inverses, and those are basically the integer axioms, plus what makes the rationals a field are the fact that every non-zero rational number has a multiplicative inverse. Okay, and so that's what makes it a field. Every non-zero value, every non-zero rational has a multiplicative inverse. Okay, and so we call those sets fields. The integers are not a field. Okay, so the set of integers is not a field because we don't have multiplicative inverses. There's no multiplicative inverse of 2, say. Okay, the set of integers mod n, it turns out, is a field if and only if n is prime. I think in the homework I ask you to show that the integers mod 7 are a field. Maybe I ask you whether it's a field or not. I guess I'm telling you now it is a field. You still need to kind of justify why it is that it's a field. Again, remember, being a field means that every non-zero element has a multiplicative inverse. So what that means you have to show for the integers mod 7 is that the numbers 1 through 6 all have multiplicative inverses. Okay, and so the rationals are an ordered field. By the way, the integers mod n are a field, but they're not ordered. There's no ordering that you can put on that. I'll let you kind of think about why that is. So I think at this point we're finally ready. Now that we understand the rationals, we're finally ready to talk about how to construct the real numbers. And I'm going to use a construction by a mathematician named Richard Dedekind. And these are called Dedekind cuts. So we're going to use what are called Dedekind cuts to construct the set of real numbers. The tricky part about the real numbers is that let's take a step back here. It turns out that if I wanted to look at some sort of an equation like 3x plus 2 equals 0, you can't solve that in the integers. There's no integer solution, but there is a rational solution, namely negative 2/3. And likewise, if I take x squared minus 2 equals 0, there's no rational solution. We need something kind of beyond that. And so the rationals are what are called incomplete. And the idea here is that there's no way, if I were to take x squared minus 2 equals 0, there's no way to describe that solution as a rational number. But also if I need to be a little bit careful here. If I take the limit of a sequence, and I know we haven't talked about limits and we haven't talked about sequences, but just intuitively, I think from calculus you can understand what I'm going to say here. If I take the limit of the sequence 1, 1.4, 1.41, 1.414, and each step I'm getting closer to square root of 2, when I take the limit of a bunch of rational numbers, I get a number that's outside the rationals. And so that's a problem that's called incompleteness. And so what we want to do is we want to kind of fill in the gaps, and we want to look at how do we kind of fill in the gaps appropriately, but in a rigorous way. There's no way to talk about filling in the gaps here without, first you need to know that there are gaps. And so the tricky part here is how do you talk about the irrational numbers without kind of assuming that they exist in the first place, right? You have to be really rigorous and really careful here. And that's why this method of construction is named after somebody, is because it's hard. Okay, so coming up with a rigorous construction of the rationals turns out to be hard. Now, the way that I want to think about Dedekind cuts is, let's first tell you what a cut is. And actually, before I do that, just a little bit about boundedness of sets. This is probably review. This is probably something that you know already. But given an ordered set, so if I have any ordered set S, and say it has an order that I'm just going to call less than, whatever that means for the given set, a set is bounded above. So a set S is bounded above if there exists a value m so that x is less than or equal to m for all values x in S. Okay, and so an ordered set S is bounded above if there exists such an m. M is called an upper bound. So m is an upper bound of S. And we might say S is bounded above by m. Now, bounded below is similar. I'm not going to write it out. A set is bounded below if there exists a value m so that x is greater than or equal to m for all x in S. And then in that case, we say x is a lower bound of S, or we would say S is bounded below by m. Okay, so I'm not going to bother to write that. And then a set S is bounded if and only if it's bounded above and bounded below. So to be bounded means that S is bounded above and bounded below. Okay, so again, just some definitions there. Probably I should be a little bit more careful here. Let me actually take one thing back just to make it clear. Let me amend my definition just slightly. Let's let E be a subset of S where S is ordered. Then the set E is bounded above if there exists a value m in S, so that x is less than or equal to m for all values in E. Okay, sorry for the change there. Okay, so let's let E be a subset of an ordered set S. I think that this definition is just a touch clear. Let E be a subset of an ordered set S. Then the set E is bounded above if there exists a value in S that kind of is the upper bound for everything. Okay. All right. Just to give you an example, if I take the set A, which is the set of all the rational numbers, such that x squared is less than 2, this set is bounded above by, say, 1.5. Right, if I take the real number by 3/2. So if I take 3/2, then that's going to be an upper bound. It's also bounded below. This set's bounded below by negative 1.5. It's also bounded above by 2, bounded above by 3, bounded above by 10. It doesn't really matter what the bound is. We just care that there is kind of an upper bound to it. Likewise, this is bounded below by negative 1.5. So A, being a subset of the rationals, is bounded. Okay, so A is what's called a bounded set. All right. Again, just a few definitions. I'm going to let E be a subset of S, where S is ordered. Then we're going to say that a value beta in S is called the least upper bound. So the least upper bound of E. If beta is an upper bound of E, so in other words, x is less than or equal to beta for all x in E. Every value in E is bounded above by beta. And to say it's the least upper bound means that there are no upper bounds that are smaller. So like I said before with our example, 1.5 is an upper bound, 2 is an upper bound, 3 is an upper bound of this set. And so we have lots of upper bounds, but what we're interested in is the least upper bound. And so what makes it the least is that if you have a value, let's call it alpha, so if you have a value alpha in S with alpha less than beta, then alpha is not an upper bound of E. So to be the least upper bound means that beta is an upper bound of E, and anything smaller than beta is no longer an upper bound of E. So just to give you an example or two, if I take the set of rationals, where, say, this is the set of rationals that are less than 2, then the least upper bound, by the way, the least upper bound also has another name. It's called the supremum. So the supremum of A would be 2. And the idea is that 2 is an upper bound of A. So 2 is an upper bound of A because everything in this set is by definition less than 2. And 2 is the least upper bound. If I pick any value less than 2, there's going to be something that in A that we miss. And so if we pick 1.9, then we miss 1.95. If I pick 1.99, then we miss 1.995. Right? No matter what value we pick less than 2, there's going to be something that we miss. So we would say that 2 is the supremum of A, or the least upper bound. Okay, and so that's one example. Another kind of mundane example that's maybe even a little easier than the one before. If I have the set of rationals where x is less than or equal to 2, then the supremum, or least upper bound of A, is also 2. Because 2 is an upper bound, everything's less than or equal to 2, and anything less than 2 won't be an upper bound of A. So those are two examples there. Finally, if I take the set A, which is the set of rationals that we were talking about before, where x squared is less than 2, it turns out that here the supremum of A, we want to say that the supremum of A is square root of 2, but the problem is that square root of 2 isn't a rational number. It's not rational, and so we can't talk about square root of 2 as being a supremum for the set because we need to be in the set of rationals to begin with. So the supremum of A does not exist. So until we think of the rationals as being a subset of a more complete field, which we'll call the reals, we can't talk about square root of 2 being a supremum. So the supremum of A does not exist as a rational number. There is no rational number that's the supremum of A. And just a nice argument here, let's suppose that gamma is the supremum of A, okay, so let's say gamma is a supremum of this set and gamma is rational. Then what we could do is we could consider the number beta, which would be gamma minus gamma squared minus 2 over gamma plus 2. And then you can check that beta is rational. You can check that beta is greater than gamma. And you can check that beta squared is still less than 2. So in other words, no matter what rational number you start with, you can always find a larger rational number that's still satisfying that gamma, that still satisfies this inequality. So there is no largest rational number that satisfies that inequality. So there's no, what did I want to say? I want to make sure I said that correctly, so I'm going to say it again. There's no supremum of this set. There's no least upper bound that's rational. Any upper bound of this set will not work. Okay, so it doesn't work. So you can always find a rational number that's either smaller than the upper bound, or if you pick a smaller bound, it might not be an upper bound anyways. Okay, I think I might have said that in a confusing way, but anyways, the point is that if I take the supremum of this set, then the supremum can't be rational. All right, enough of that. So what I want to do, and this really is the big problem that we have with the rationals, is that we have sets in the rationals where the supremum doesn't exist as a rational number. Okay, and so this set has no supremum. That's called incompleteness. So since the supremum, let me give these names A1, A2, A3. Since the supremum of A3 doesn't exist, we say that the rational numbers, this set is incomplete. Okay, and so that's the problem that we're trying to fix. Okay, so that's bad news for analysis. That means that if we were to do things like trying to calculus over the rationals, we'd have big problems because maybe we would have functions where there are no maximums anymore, right? We could talk about, say, derivatives of functions defined over the rationals, and then we're going to have problems because we'll have the problems like we had before with the limits, where the limit might not exist in the rationals anymore. We can have problems like this where we don't have a supremum anymore. And so we need to be a little bit careful here. And so what Dedekind proved was that there is a unique, so there exists a unique ordered field, R, containing Q, with what's called the least upper bound property. The least upper bound property just means that R is going to be a field such that every supremum exists as a real number. Okay, so the least upper bound property means that every set has a supremum. Every set has a least upper bound. Okay, so that's the least upper bound property. And so here's how we're going to describe the set. Here's how we're going to construct it. We're going to define a cut as a particular subset of the rationals. And the subset of the rationals that it's going to be is going to have three properties. So the first property is that it's a non-trivial subset. So alpha is not allowed to be empty, and alpha is not allowed to be the whole set of rationals. Alpha is going to be what's called closed downward. So what I mean by that is that if there's a rational number in the set, then every smaller rational number is also in that set. And so this means that if x is a rational number and x is in the set, then for all rational numbers that are smaller than x, then those are also in the set, alpha. Okay, and so what this means just graphically, just to make a little bit of sense of this, is that if you talk about all of, now I'm just talking about the rational numbers for now, but if you talk about the set of rational numbers, as soon as you have any rational numbers in the set, you have all of the rational numbers that are smaller than that all the way to negative infinity. Okay, and so that's what I mean by closed downward. And then the third property that cuts are going to have is that the supremum of the cut is not allowed to be in the cut itself. Okay? And so, just again, by way of example, I think just to make a little bit more sense of this, if I look at a few particular sets, let's talk about whether or not they're cuts. So if I talk about alpha being the set of rational numbers such that x is less than or equal to 2. This is not a cut because the supremum of the set is 2, as we discussed, and 2 is in alpha. It's not allowed to be. So we're only saying that a set is a cut if the supremum is not in there. So if I wanted to make that a cut, I would have to talk about the set of rational numbers that are strictly less than 2. This is a cut. If I talk about the set of rational numbers where x squared is less than 2, the supremum of the set doesn't exist, so it's not an alpha, so that part's fine. But it's not a cut because it's not closed downward. Okay, this is actually a bounded set. It's bounded above and below. The bounded below part is the problem. Okay, this doesn't satisfy property 2. It's not closed downward. So for example, 0 is in the set, but negative 2 is not. Okay, so here we have an example of a value in the cut, but smaller rational numbers are not in the cut. So that's not a cut. It doesn't satisfy part 2. If I wanted to make it a cut, what we would have to do is we'd have to talk about all of the rational numbers where x squared is less than 2, or where x is negative. And then it is a cut. Okay, and then the way that we define the real numbers are defined as the set of all of the cuts of rational numbers. So alpha is a cut. So that's how Dedekind defines the reals. And so let's think about in what sense is the set of rational numbers in the reals when we define the reals this way. And it turns out that given a rational number, let's say x, no, let's not use x. Given a rational number r, then the real number that kind of represents r, represents is a loaded word. I don't mean that in any, there's a thing called representation theory. I'm not talking about anything like that. I'm just saying the value that kind of plays the role of r is the cut. It's the set of rationals where x is strictly less than r. Okay, and so in that sense, this cut represents the rational number r. There's other cuts, though, that represent things that are missing. So, for example, now we can fill in and talk about square root of 2. So the number square root of 2 is represented by, or is portrayed by, this cut of rationals where x squared is less than 2 or x is less than 0. So that's a way that you can represent the irrational number square root of 2. Okay, so square root of 2 is represented there. And so what I want to do is I want to talk about, given this kind of weird construction of the reals, how do we define addition and multiplication? Addition is easier. So addition is easier. So if I want to talk about the addition of two cuts, say alpha and beta, this would just be what's called the Minkowski sum. This is the set of pairwise sums x plus y, where x is in alpha and y is in beta. And importantly, what matters here is that we define addition and multiplication in a way that respects addition and multiplication of rationals, right? We want to, since we're already including the rationals in our set, we want to do this in a way that respects addition and multiplication of the numbers that we already know. So for example, if I take the cut corresponding to, let me do this on a new page. If I take the cut corresponding to, say, the real number 2, so that would be the set of rationals that are strictly less than 2, and I add to it the set of rationals that are strictly less than, say, 5, then what I want to do is I want to get the rational that's strictly less than 7. And in fact, that's exactly what we get. Because what we're going to get here is we're going to get all of the rational numbers up to 2. So all the values up to but not including 2. Okay. And we'll have all the values up to but not including 5. And then to get a value in the sum, what we're doing is we're picking a value in this first sum and picking a value in the second sum, and we're adding them up pairwise. That'll give us a value in the sum. And so we can do this for all pairs of points in the first set and the second set. And when we do that, what we get is exactly the set of rational numbers up to but not including 7. So in this way, the addition of reals respects addition of rationals in the usual way. Multiplication is a little bit trickier. You cannot just do pairwise multiplication, because if you were to take 2 times 5, for example, because you have the negatives, you would get arbitrarily large values. Okay, and so you have to be a little bit careful there. But what you can do is you can first define multiplication for positive reals. So if alpha and beta are positive, then this is going to be the set, well, let me say it this way. The product of the cut A and B, alpha and beta, is going to be the set of rationals where, it's going to be the set of products x times y, where x is in alpha and x is greater than or equal to 0. Y is in beta and y is greater than or equal to 0. And then we're going to take that set and union it with all of the rationals. Let me not use x again. Let's use all the rationals that are strictly less than 0. So then we'll put back all of the values that are less than or equal to 0. So now what we're going to do is to define the product of 2 and 5, we're going to cut it off at 0. And now we can talk about all the pairwise products of one cut with another. That gives us the numbers from 0 to 10. And then we put back the negatives. Okay, we put back the negatives there. So that's how we define multiplication. It's a little bit fiddly, but it's kind of what it is. Let's also talk about additive identities and multiplicative identities. So additive identity is going to be played by, so the additive identity is the cut, which I'm going to call 0 star, which is the set of all of the negative rational numbers. Okay, so that's how we get 0. And then if you think about kind of defining addition in the way that we did, then you know that alpha plus 0 is just alpha. Okay, and so that's the additive identity. There's a multiplicative identity. The multiplicative identity is the cut corresponding to the rational number 1. So this is the set of the rational numbers where x is less than 1. And then if you walk through kind of the, if you walk through this definition of multiplication, you see that alpha times 1 is going to be alpha. And you have to kind of consider different values of alpha. When alpha has positive values, when alpha only has negative values, you have to be a little bit careful there. There's additive inverses. So every cut has an additive inverse. So the additive inverse of alpha is the set beta. So alpha is going to be some cut. The additive inverse is going to be the cut beta, where alpha plus beta give you the 0 identity, give you the 0 element. Okay, and then we denote beta by minus alpha. So for example, if we talk about, let's think about how I want to do this. If we talk about the set, this is really easy to do with rationals. So if I have a cut that represents a rational number, say 5/3. So if I have a cut that represents the rational number 5/3, if that's our alpha, then minus alpha is just going to be the set where x is less than negative 5/3. Okay, and so that's how that's going to work. Now, if I have a cut that does not represent a rational number, now it represents something new, like square root of 2, for example, then we have to be very clear about how we define the additive inverse. And so in general, again, this is a little bit, this is pretty technical stuff, but the way that you can define an additive inverse, let's just talk about the general definition here, and then we can think about it in terms of stuff that we know. Given a value a, minus a is going to be the set of all of the rational numbers such that there exists a value epsilon greater than 0, where negative x minus epsilon is no longer in alpha. And so let's think about what this means. If I have this cut that corresponds to 5/3, then its additive inverse is, of course, this cut, all the rationals that are less than negative 5/3. And so another way that you can describe this set is that you can think about all of the rational numbers such that there exists an epsilon where negative x minus epsilon is no longer in alpha. And so let's think about that. Let's think about all of the rationals where if I take negative x minus epsilon, it's not in the original set. So for example, if I were to take, let's say, the number -1. So, no, -2. Let's say -2. So -2 is in minus alpha since there exists an epsilon such that if I take -2 minus epsilon, that's no longer in alpha. And let's just unpack that. -2 minus epsilon is saying that 2 minus epsilon is not in alpha. And indeed, I can find a value of alpha, epsilon, like 1/10 or something, where 2 minus that is no longer in alpha. So the additive inverse is exactly these elements with that property. Again, a little bit technical, but that's the way that we can define additive inverses in general. Multiplicative inverses are, again, a little bit tricky. So maybe I'll talk about that in class I don't have a general definition. I want to have that nailed down before I share it. Multiplicative inverses we need to be a little bit careful of. We want to find, it turns out that for every, let me just tell you a few things here. For every cut, so if alpha is a cut, and as long as alpha is not the 0 element, then there exists a cut beta so that alpha times beta is equal to 1. And again, when the cuts represent rational numbers, then everything is fine, and it's pretty straightforward about what we mean. If the cuts represent new numbers, like irrationals, then we have to be a little bit careful. And I'll either add on to this video or I'll talk in class on Monday about how exactly you find those multiplicative inverses. But the fact that every non-zero real number, every non-zero cut, has a multiplicative inverse is what makes, that's what makes the set of real numbers a field. Okay, and so that's what makes them a field. Finally, if I were to have a cut, say alpha 1, alpha 2, and alpha 3, then I want to talk about how could we find the supremum of them. How could we find the supremum of alpha 1, alpha 2, and alpha 3? Okay, so if I want to talk about the supremum of the set, turns out that the way that we do that, if I want to talk about the supremum of, say, the cut corresponding to the numbers 2 and 5, if I talk about the supremum there, the biggest number, I'm kind of comparing this to, if I want to talk about the maximum of, say, 2, 1, and 5, how do we find the maximum? Well, it's the biggest number, it's 5. How can we do that if we're talking about cuts? Well, what we can do is just take the union of all of these. So we would take the union of the alpha i's, in this case from 1 to 3. And it turns out if we do that, then we get the supremum, or the maximum of these cuts here. The supremum is the maximum because this is a finite set. All right, so that is how Dedekind defined the real numbers. The real numbers are exactly the set of cuts of rationals. And what this does is this fills in all of the gaps that we have in the rationals. Again, this is a very formal way of looking at the real numbers. And so when we talk about the real numbers in class, we're not going to think about them as particular cuts. That's a really tedious way to think about real numbers. We'll just go back to thinking about them as kind of the standard real numbers. But I think it's a nice thing to see at least once in your mathematical career, right? How to define the reals and what makes the reals kind of a weird set. And so that's what I got. All right, thanks for watching the video, and I will see you all on Monday.